Hello, Phys4C people. This is Lab 7 lecture on thin lenses. We're going to use this simulation called the ray optic simulation to run these online labs for this week on lenses and next week on mirrors. In order to do these labs, you must have seen the online video lectures that I posted on YouTube. I'll guide you as we go along, but you have to look at those before you start this lab. Okay, so let's review briefly what we know about ray optics. There are two types of lenses, converging and diverging lens. We always identify the near and far focal point and the two F points, and they're always symmetric for thin lenses. If the focal point or focal length is positive, we call it converging. If the focal length is negative, we call it diverging. And these rays always start from the left and go to the right. Only when the rays are parallel to the central axis will these rays cross at the focal point. So a converging lens has a positive focal point, but if you look at a diverging lens, it diverges the rays, but if you follow these rays backwards, it appears if all of the light is coming here. In part 1 of the lab with John, he has a video that actually goes through this process. The two main equations that we will use throughout the lab is the thin lens equation and the magnification equation. For the thin lens equation, it relates the focal length, S the object distance, and S prime the image distance using the equation 1 over F equals 1 over S plus 1 over S prime. The key point with the thin lens equation here is that if the S prime is positive, then it's a real image and on the right side of the lens. If S prime is negative, then it's a virtual image and it's on the left side of the lens. The magnification equation is packed with a lot of information, so let's write that down. The lateral magnification is equal to the negative of the image distance over the object distance. And there's two pieces to the magnification equation, the sign and the magnitude of the magnification. If I focus on the sign, if this quantity has a minus sign, then that means that I have an inverted real image. On the other hand, if I have a plus sign, then the image is erect and virtual. For the magnitude, if the magnitude of the magnification is less than 1, then we know we have a smaller size image. If it's equal to 1, we know it's the same. And if it's greater than 1, then we know that the image size is going to be larger. Ray diagrams for lenses. From our online discussions, there are two principal rays that we use, ray 1 and ray 2. Ray 1 goes parallel to the central axis and then refracts through the lens to the focal point. Ray 2 goes through the middle of the lens. Where the rays cross, an image is formed. Let's look at these rays. Start off with an object that has a height of 1 square in orange for both of these lenses here. Let's draw ray 1 for the converging lens. If I look at ray 1 for the converging lens, you could see that it crosses the focal point on the other side. Now let's do it for the diverging lens. For a diverging lens, you could see that it still goes parallel, but now it diverges away, but if I follow this back, it goes to the negative focal point, whereas this one went to the positive focal point. Now the second ray always goes through the middle, and it's the same for both. You could see that ray 2 for both of them just goes right smack through the middle of the lens. So where the rays cross is where the image is formed. If you look at the image characteristics of this image for the converging lens, you could see here that the arrow is inverted. It's larger because it's larger than 1 square, and because it's on the right side, it's real. And if you look at the diverging lens, the image is clearly erect, smaller, and because it's on the left side of the lens, we say that it's virtual. A big part of today's lab is actually being able to recreate these rays. So let's go to the ray optics simulation to show you how I can set that up. So here I am in the ray optics simulator, and I want to generate the primary or principal rays, ray 1 and ray 2, to form images. So how do I do it here? So first thing that I would do is I would set up a grid system. Okay, now that I have a grid system, the second thing that I would do here is that I need a ruler to be able to measure things. So here's my ruler, and what I would do here is that I would shoot for the middle of the screen, and I would go all the way across. Now, to get the numbers to work out well, you want to line up this ruler with one of the grid lines that's horizontal. And what I'm seeing here is that I typically put a value in the middle of this thing here, and I'm going to say that since this goes all the way across to 1200, I'm going to say that 600 here is going to be my middle. Now the next thing that I want to do here is that I want to put in a lens. So if I go to the glasses and I get an ideal lens, I want to take this lens and I want to line it up with the vertical axis of one of the grid marks, and I want to put the middle, the tick mark in the middle, to line up. Now you can adjust this thing here so that it's vertical, and again that helps with the numbers. So now I have a system where I have a long lens, I have a ruler, and so now to set up ray diagrams, I'm going to adjust the focal length of this guy by clicking here at the focal length, and I can change that just by clicking it, but let's say that this is 100. And then the next thing that I need here is I need to set up my object. An object has two things. It has a distance from the a distance from the lens, and it has some height. For the sake of argument, let's say that the object is going to be 300 centimeters away. So if I come in and I pick on a ray, I have a point here, and so you could see that this point here is at the 300 centimeter mark, but it also has to have some height. So I'm going to come in and get a second ruler, and again, it pays to adjust this thing so that it's along the vertical axis. Now I'm going to take this point and I'm going to say that my object is 100 centimeters high. Now I could come in here and I should be able to adjust my ray so that it's parallel to the axis. And what you're seeing right now is that if I click on this lens, note that this guy is not going to the 100 mark of the focal length. So I keep adjusting my lens until it's in the middle, and once I do that, I now get 100 centimeter focal length as this thing indicates. So now what I want to do here is that I want to come in, and add a second ray, and this ray here I need to put at the exact same location, which is at 100, and then I'm going to adjust it so that ray number 2 goes through the middle of the lens. So what you're seeing here is that I have an object of this height and I have an image where they cross. Now there's this thing called a blocker, and this blocker, we can use this thing as either to represent objects. So let's say that this object then is going to have a height of 100 centimeters. Now I'm not going to put that at the 300 centimeter mark because it's a blocker, or in everyday language it's called a screen. And then I could adjust this blocker or screen, and you could see that if I put it there, it blocks the rays, but I can adjust it so that it tells me where the rays are going to be in focus right here. So just sort of like playing with it a little bit. Then what I find here is that I could measure the height of this image. I could measure the distance to this image with the ruler here. So if I add one more ruler, I could then come in here and I can do this to measure the height of this image now. So now I have a way of measuring not only the object distance, the object height, but also the image distance and the image height. Now the second thing that we got to focus on here is diverging lens. So the way to deal with diverging lens is that you could click on the lens and then come in here and put in -100 to get a diverging lens. And if you do that, you could then extend ray 1 back through, and then you still have the one going through the center, and you could see where the image is being produced now is on the left side of the lens, indicating that it's virtual here. So that being the case, I could do the same thing as before. I could measure the distance to the image. I could move my ruler so that I could measure the height of this image, and therefore I could measure two quantities about this, about the image here. Now to organize my information into a table, I have the focal length. I could measure where the image is experimentally. That means using the simulator. I could measure the height of the image from the simulator. And then using the thin lens equation, for my calculations, I calculate the image location, and then I predict the image height. And then just eye these two and these two and just see how they went. That is, are they really close? Or is there some mistake that you have to go back and fix? Okay, let's go to part 3. Here's a single, more complex situation for a converging lens. The only information that's given to you is that the focal length is 200 centimeters. The object height is 100 centimeters. So what we do know now is that the magnification is set at -2. So what we want to do now is that we want to predict the object location and the image location and the height of the image. The way we do this is we set up two equations with two unknowns. So this is one piece of the information, that the magnification is -2, but we know that the magnification is -s prime over s. From the thin lens equation, we know that we're also relating s and s prime. Solve these two equations for s, s prime, and the height image. Once you have that, then go to the ray optics simulator and check to see how you did with your calculation. That is, set up an object with 100 centimeters from the lens. Excuse me. That means with your predicted object location, and that set the height to 200 centimeters, and see if the image has a magnification of -2. In other words, if it has a magnification of -2, that means that the object that starts off at 100 centimeters should have an image that's 200 centimeters. See if your calculations actually show that. Part 4, Two-Lens System. You must have watched the Phys4C lecture 34.7 on YouTube that focuses on two-lens systems before you do this part of the lab. And the way we do this, as we do in my notes, is that we break it up into two pieces. We focus on lens 1, and then we focus on lens 2. Here we go. For lens 1, I know that the object is 300 centimeters from the lens that has a focal point of 100 centimeters. The height of the object is 100 centimeters. So I have my f1 and f1 here, the near and far focal points. Using the thin lens equation, predict the location of image S1 prime. So I predict it and then go in to the simulator and measure what that image is in the simulator, and then compare them. Just look at them and just say, is it close or pretty far off? And then calculate the image height. The way I calculate the image height is from the previous example, where the image height is equal to the magnification of 1 times the object height. So the experimental one is the one you get off the simulator. This is the one where you actually do the calculation. So now I'm going to repeat this process with lens 2. In lens 2 here, I'm going to put a second lens that's diverging, that's 100 centimeters to the right of lens 1. So when I put that lens there, you're going to see that the image of lens 1 becomes the object of lens 2. But that object is going to be virtual. That means it's going to be on this side of the lens. So when I mathematically calculate that, this object S2 is negative, not positive. Again, review my YouTube Phys4C lecture 34.7, where we deal with virtual objects. So now that I have the object location for lens 2, go predict the image location and the height of the image. And then complete the table up here. Now the one thing that you want to pay attention to here is that the height of the image is the total magnification times the height of the object, where the total magnification is M1 times M2. Then go and use the ray optics simulator to measure the image location and the height of the image and see how they compare.